So let's talk about the acceptance angle and acceptance cone. So acceptance angle is used to characterize the optical fiber. Is called the acceptance angle of fiber. It is the maximum angle to the axis of the fiber that light entering the fiber is guided in the core. So we got this condition from the last slide, that theta I maximum is equals to sine inverse of under root n1 square minus n2 square. So if you are sending the light from greater than this angle, then the total internal reflection condition would not be met. So the incidence angle from air has a limitation, and that is called as acceptance angle of that optical fiber, and the formula is given by this. Okay. Then if you go into 3 dimensions, right, so there would be a acceptance cone, right, and it would be twice of that, because one side is this theta I max and other side is this. So we are making a cone of this, so the maximum angle would be twice of theta I max. So this is the acceptance cone angle. Okay. Okay, we can move on now to the numerical aperture. So numerical aperture has a very useful parameter for characterizing the optical fiber. So it can give you a idea about measure of light collecting ability of fiber, because if a light is coming from more than this angle, it won't get totally internally reflected, right? So this puts this acceptance angle and acceptance cone puts a foundation or limitation on optical fiber light capturing ability and to transmit it to the other end. Okay, so this can be characterized by a figure of merit, or whatever you say, numeric called as numerical aperture. Okay, and it is given as sine theta a, and this formula we already have got, that is under root n1 square minus n2 square, where n1 is refractive index of core and n2 is refractive index of cladding. So numerical aperture varies from 0.12 to 0.20 for single mode fibers, and 0.20 to 0.50 for multi-mode fibers. Okay, so these are some values that you should remember. Okay, and there is this last part, that numerical aperture can have another formula which we can get from fractional index difference, which is the ratio of the difference in the refractive index of core and cladding, that is n1 minus n2, with respect to refractive index of core, that is n1. So this fractional index difference is n1 minus n2 by n1. So numerical aperture was under root n1 square minus n2 square. Okay, so you can write it as n1 square minus n2 square can be written as n1 plus n2 n1 minus n2, and you can multiply and divide by 2n1. So I have divided here and I have multiplied 2n1 here. So because n1 plus n2 by 2 is almost equals to n1, we are using this approximation. So this was this n1 plus n2 by 2 can be replaced by n1, and the remaining thing is n1 minus n2 upon n1 into 2n1. So 1 n1 n1 cancelled, so it becomes n1 minus n2 into 2n1, and numerical aperture was under root n1 square minus n2 square. So this becomes n1 minus n2. Okay, you don't cut it here. If you take it as del, this thing, so this can be replaced as del, and you have 2n1 still here, and this n1 and this n1 will make n1 square. So we have this thing, so this is del. So okay, so this is n1 square minus n2 square, because it was not having a square root. So when you go to find out numerical aperture, you have to put it inside a square root. So it will become del 2 n1 square inside the square root. So this is the formula for numerical aperture, important formula. So you have two formulas actually for numerical aperture, and you can use one of them while solving for the answer in numericals. Okay, I would be doing the V number in the next slide, because this slide